distributed file system works along with MapReduce. The data is written on and read by disks. MapReduce jobs require a lot of disk read and write operations, which is also known as disk I/O, or input and output. Reading and writing to a disk is not just expensive, it can also be slow and impact the entire process and operation. This is specifically true for iterative processes. Hadoop is built for write once, read many type of jobs, which means it's best suited for jobs that don't have to be updated or accessed frequently. But in several cases, particularly in analytics and machine learning, users need to write and rewrite commands to access and compute on the same data more than once. Every time such a request is sent out, MapReduce requires that data is read and/or written onto disks directly. Note that though the time to access or write on disks is measured in milliseconds, when you are dealing with large file sizes, the time factor gets compounded significantly. This makes the process highly time-consuming. In contrast, Apache Spark uses resilient distributed datasets, or RDDs, to carry out such computations. RDDs allow data to be stored in memory, which means that every time users want to access the same data, a disk I/O operation is not required. They can easily access data stored in the cache. Accessing the cache or RAM is much faster than accessing disks. For instance, if disk access is measured in milliseconds, in-memory data access is measured in sub-milliseconds. This radically reduces the overall time taken for iterative operations on large datasets. In fact, programs on Spark run at least 10 to 100 times faster than on MapReduce. That's why Spark is gaining popularity among most data scientists, as it is more time efficient when it comes to running analytics and machine learning computations. One of the main differences in terms of hardware requirements for MapReduce and Spark is that while MapReduce requires a lot of servers and CPUs, Spark additionally requires a large and efficient RAM. Let's understand resilient distributed datasets in detail. As you have already seen, the main programming approach of Spark is RDD. RDDs are fault-tolerant collections of objects spread across a cluster that you can operate on in parallel. They are called fault-tolerant because they can automatically recover from machine failure. You can create an RDD either by copying the elements from an existing collection or by referencing a dataset stored externally, say on an HDFS. RDDs support two types of operations: transformations and actions. Transformations use an existing dataset to create a new one. For example, Map creates a new RDD containing the results after passing the elements of the original dataset through a function. Some other examples of transformations are filter and join. Actions compute on the dataset and return the value to the driver program. For example, reduce aggregates all the RDD elements using a specified function and returns this value to the driver program. Some other examples of actions are count, collect, and save. It's important to note that if the available memory is insufficient, then Spark writes the data to disk. Here are some of the advantages of using Spark. It's almost 10 to 100 times faster than Hadoop MapReduce. It has a simple data processing framework. It provides interactive APIs for Python that allow faster application development. It has multiple tools for complex analytics operations. These tools help data scientists perform machine learning and other analytics much more efficiently and easily than most existing tools. It can easily be integrated with the existing Hadoop infrastructure. PySpark is the Python API used to access the Spark programming model and perform data analysis. Let's take a look at some transformation functions and action methods which are supported by PySpark for data analysis. These are some common transformation functions. Map returns RDD formed by passing data elements from the source dataset. Filter returns RDD based on selected criteria. Flat map maps items present in the dataset and returns a sequence. Reduce by key returns key value pairs where values for each key is aggregated by a given reduce function. Let's now look at some common action functions. Collect returns all elements of the dataset as an array. Count returns the number of elements present in the dataset. First returns the first element in the dataset. Take returns the number of elements as specified by the number in the parentheses. Spark Context, or SC, is the entry point to Spark for the Spark application and must be available at all times for data processing. There are mainly 4 components in Spark tools. Spark SQL. It's mainly used for querying the data stored on HDFS as a resilient distributed data set, or RDD, in Spark through integrated APIs in Python, Java, and Scala. Spark Streaming. It's very useful for data streaming process and where data can be read from various data sources. MLlib. It's mainly used for machine learning processes such as supervised and unsupervised learning. GraphX. It can be used to process or generate graphs with RDDs. Let's set up the Apache Spark environment and also learn how to integrate Spark with Jupyter Notebook. First, visit the Apache link and download Apache Spark to your system. Now use 7-zip software and extract the files to your system's local directory. To set up the environment variables for Spark, first set up the user variables. Click New and then enter Spark Home in the variable name and enter the Spark installation path as variable value. Now click on the path and then click New and enter the Spark bin path from the installed directory location. Now let's set up the PySpark Notebook specific variables. This will integrate the Spark engine with Jupyter Notebook. Type in PySpark. It will launch a Jupyter Notebook after a while. Create a Python notebook and type in sc command to check the Spark context. In this demo,